So yes, as I was saying, you assume the thickness at this point, your hub thickness. And you will use this hub thickness along with your shaft radius, along with your key thickness to find your radius, and then your radius will be then used to calculate your force. So your force will be equal to the torque divided by the radius, which is this equation. Once you have your force, you will then be able to calculate your required hub thickness. Again, we have the tensile strength of the material, and this is mild steel, should be equal to the force applied divided by the area. This is the area of the hub, not force. Force divided by the area of the hub. Okay. And now the tensile strength of mild steel is up here. Tensile strength, 35 megapascals. (35 megapascals) is equal to whatever the force is you got here, divided by the area, and the area we have is going to be the length of our key. So this dimension, length of the key, and the thickness here, multiplied by the hub thickness. And now we just make the hub thickness the subject of the formula. And our hub thickness will be equal to the force divided by the tensile strength, 35 megapascals, multiplied by the length of the key. And once you get your hub thickness, that is the end of your hub analysis. Any questions up to this point? Any questions? No. Okay, great. So moving on, we've covered 3 analysis types. We just have the flange or the web and the bolt analysis to go. So now we come to flange analysis or the web analysis. What type of forces are we expecting here? This part is twisting. Okay, zoom in. Right, the force is acting in this direction with our radius here, or our distance, and the torque being applied here to try and counteract that thing. The force is reacting in that direction. So what kind of force are we expecting here? So for the key, we had a shear force. For the hub, we have a tensile force. For the web, we have a shear force. Shear force. So we'll be looking at the shear strength or the shear stress to help decide our design. All right. So shear stress of the web will be equal to the force on the web divided by the area of the web. The area, by area I mean this red zone. This is the area. Okay, it's a curved surface. So what do we do with curved surfaces when we're trying to find the area? We try and make it just a rectangle. we need to find this thickness. This is the flange thickness or the web thickness. And do we know this distance? Say this is the circle, and we're just straightening this out to be a flat rectangle. Okay, uncurling it, making it flat. So what is this distance here? It's the perimeter of a circle, the perimeter of the circle. And how do you find the perimeter? Or the circumference of the circle? 2 pi r, or pi times diameter. Now what's our diameter in this case? Again, remembering the area is equal to the thickness of the web multiplied by 2 pi r, or let's just type this as pi times diameter. This is diameter of what? What diameter is this? This diameter is the diameter of our boss, yeah, or of our hub. Yes, very good, Shivnu. So our diameter will be equal to the shaft diameter, or sorry, no. Let's just find the radius first and multiply it by 2 to get the diameter. So the radius will be equal to the shaft radius plus the thickness of our key above the profile of the shaft. So that is our key thickness divided by 2 plus our hub thickness, or our hub thickness that we found in our hub analysis. That will give us our radius, and then our radius multiplied by 2 will give our diameter. And this diameter we'll use in this formula. Okay, we still don't know our force on our web. So how do we find our force? Like how we've been doing all along, we do torque times force multiplied by distance. Distance in this case is what? Torque, we know it's 47.46. We need to find our force. And what's our distance in this case? From the center to the very edge where the force is being applied. So from our center to where this is being applied, this is our distance. And that distance is the radius of our boss. So this diameter divided by 2, or we could just have the radius. All right. From here, we can now make FW the subject of the formula, so the force on the web, and then use this force back substituted. Into this equation. And we will find our thickness by making the thickness the subject of the formula. Right? Any questions up to this point? Our shear strength or our shear stress of the web. Remember, our web is made out of cast iron because our web and our boss, they're all made from the same material, which is cast iron. And the shear strength for cast iron is given up here. Cast iron shear strength is 5 megapascals. So we substitute that into our formula. And we can find our thickness of our web, which is our web analysis. And the last one is the bolt analysis. Bolt analysis is basically how far are you going to place your bolts? So decide the PCD, or the pitch circle diameter, and how many bolts are we going to use, and what thickness. We've already been told the grade of bolt that we have to use. So the grade of bolt that we have to use is 4.6, and we're given the data sheet here. So it's all the information is given here. Now we just need to decide how many bolts we want to use and where we want to put them. So for the PCD, it's basically an assumption. The assumption is based on your own common sense. So obviously the PCD, or the pitch circle diameter, has to be bigger than your boss diameter. So PCD has to be greater than your hub diameter. All right. And it also has to factor in the space for you to access it. So say to be able to access plus the distance for accessibility. By accessibility, I mean you have to be able to fit a wrench in there, or a spanner or something, to be able to loosen and tighten your bolts, yes? And this is all just a common sense or a logical estimate. So let's say that our hub diameter we found was 120 millimeters. We have to plus some kind of distance between there and the center of where the bolts are going to be, so that we can actually access them. So let's say that we add another 5 centimeters or 50 millimeters. Let's say we add 50 millimeters this side and 50 millimeters this side, so that we can access the bolts. This is the hub here, in here, and this is the distance from the hub to the center of the bolts. So 50 on either side. So now our PCD is about 220 millimeters. Let's just say that. This is an assumption. And it's all based on your own common sense and what you think is reasonable. So once we've assumed our PCD, we will now know our radius, because our radius will be half of our PCD, since this is the diameter. So radius will be equal to PCD divided by 2, which is equal to 110 millimeters. And now we have two different methods we can use. We can either say that we want to use a certain number of bolts, or we can say that we want to use a certain size of bolt. So if we use the assumption that we want to have 3 bolts. If we say we want to use 3 bolts, we have to find the diameter. And if we say that we want to use a bolt that has a diameter of 10 millimeters, we have to find the corresponding number of bolts. All right, those are the two ways that you could approach these types of this section of the question. And some of you will go for setting a certain number of bolts and finding the diameter, or some of you will say, let's find the diameter, let's set a diameter and then use the number of bolts that we have to use. Okay. First, let's find the force that will be exerted. So at this PCD, and knowing the torque, force times distance. Distance in this case is going to be our radius, which is PCD divided by 2. Our torque we already know is equal to the force on the bolts multiplied by the distance, which is PCD divided by 2, which is 0.110 meters. Our force on our bolts, we will know now. So what is that? So it'll be around 4,340 newtons. And now this force will be shared amongst the number of bolts that we have. So let's say that I want to use 3 bolts. So I'm setting this and I'm saying I want to have 3 bolts set at this distance, at this PCD, 220 millimeters, but I need to know how thick I need to make my bolts in order for it to be able to withstand the forces that it's being exposed to. What type of force will we be experiencing here? The force will be acting in this direction, which is parallel to this surface. So it'll be a shear force. So we will use the shear strength is equal to the force on the bolts divided by the number of bolts. So the bolts times the area of each bolt. And the area of a bolt, the cross section of a bolt is circle. So the area of a circle is pi r squared. And we need to find this r. So you make r the subject of the formula. Okay? Any questions? Now this shear stress. What shear stress will you use here in this case? Now it says back here in the ultimate tensile strength is 244 megapascals. This is tensile strength. All right. And if you read this bit of information about the bolts, and we have a closer look here, the allowable shear strength of the steel fastener is about 0.66 times the tensile yield strength. Now our tensile yield strength is what? 240 megapascals. And our shear strength, so our shear strength is equal to 0.66 times that 240. So our shear strength is 158.4 megapascals. And this is the value that you will use in your calculations down here. Okay, you will use this shear strength as 0.66 times 240. You've calculated your force. You've set the number of bolts, so this will be 3. And now you just find the area, and the area, then you solve to find your radius. And once you have your radius, you can find your diameter. And you match that diameter up with the information given here. Now let's say after doing that calculation, we find that the radius comes to say 5.4 mm. Let's just say example. Let's find that the radius is 5.4. So that means the diameter would be 10.8 millimeters. Now, if we look at this table, there is no size for 10.8. What's the next size that's available? Or what's the next logical size? The only other size, we can't use M10 because M10 has 10 millimeters as the, yeah, exactly, Shivnil. The only logical choice is 12 or up. So then the bolt that we will be using is M12 times 3 bolts with a PCD of 220 millimeters. And that's how you would approach these types of questions. Oh, and that's how you're supposed to approach this assignment. Okay, so the calculation report on its own is about 15 marks. And then your drawing or your AutoCAD renditions and your assembly drawings, exploded views, those are all worth 10 marks. So 15 for the calculation report, 10 for the drawings, get a total of 25 marks. Are there any questions at all about anything that's been discussed today? Any questions? Okay. So for this week's attendance, please leave your ID numbers in the chat here, and I will update it now. There's no activity that you have to do on your own. Just work on your assignments.